All right, so hello everyone, I'm Norman Wahlberger, and today in this little course on probability and statistics, we're going to talk about some special probability distributions. We're going to talk about the binomial distribution and the geometric distribution, and associated to that some interesting, pretty simple kind of test called a sign test to tell whether some situation is likely true or not. So let me remind you the general situation is we had a sample space S and we had a function on that. Okay, a function is just a random variable, and that takes values. Let's put it on the horizontal line now. Takes values on the line, and these various values that we get, say x1, x2, x3, and so on, come with certain probabilities. Right? So if we have, say, xi, then associated to that is a probability, p sub I, where p sub I is the probability that x takes on the value x sub I. Or I guess this xj would be p sub j. And what that is more technically, it's what you get if you look at the inverse image of xi. Maybe I should put xi here, and its probability p sub I. So if we look at the inverse image of xi, that would be some subset over here. So x inverse of little xi. Then that's an event in the sample space, and its probability is this pi. So it's the probability of x inverse of little xi. Okay, so we start with this situation, an experiment and a certain measurement, and out of it we get this probability distribution, which is really just a bunch of values on the line, x1, x2, x3, and so on, with certain probabilities associated to them. All right, so this is the probability distribution. Associated to x, or maybe we just say of x. And what it really amounts to is values, say x1, x2, up to xn, with probabilities p1, p2 through pn. And of course these have to be real probabilities, so they all have to be between 0 and 1. And they all have to add up to 1, so that the sum of the pi's from I equals 1 to n is in fact 1. And then associated to such a distribution, because it can be rather complicated, a lot of information in this, we have all these values and all these probabilities, we want to condense the information into just a few small, readily digestible pieces of information. And there's two primary ones. So there's the expected value, which is the sum of the xi's times the pi's. Okay, and that's usually denoted mu. That's some kind of average value somewhere in the middle of the probability distribution. And then there's the variance, which is given by summation I equals 1 to n. Well, we take xi minus mu and square it and multiply by pi. And we saw that there was an alternate way of thinking about that. An alternate way of thinking was the sum from I equals 1 to n of the xi squareds times the pi minus the expected value squared. So these are sort of equivalent or alternate ways of computing things. This is the expected value or mean, and this is the variance. And then there was a sort of a third quantity of interest that we sometimes introduced, which was just the square root of the variance, and that was the standard deviation. All right? So the standard deviation is the square root of the variance. Standard deviation. All right, one of the interesting things about studying a little bit of probability and statistics is that you start to appreciate that there are all kinds of probability distributions around us that actually have a lot to do with our lives. For example, perhaps you go to Anzac Parade to catch a bus on your way home after uni. Okay? So suppose that when you go back to Anzac Parade, you have to wait. All right, suppose you, just having taken this little short course on probability and statistics, you say, well, let's do a little experiment. Let me measure how long I have to wait for the bus. And I'll measure it in minutes so I don't have to fuss around. So it'll either be 0 minutes in case the bus is right there, or 1 minute, 2 minutes, 3 minutes. So maybe you measure every day, you make a record of how many minutes you had to wait for the bus. Okay? So sometimes the first day maybe you have to wait 2 minutes, and then the next day you have to wait 5 minutes. The next day the bus is right there, and the following day it's there as well. Then after that 2, 1, 4, 7, 31. Maybe there's a bus crash or something. Okay, and maybe it goes on like this. So you get all these numbers. But after a while, you'll realize that all these numbers are not equally likely. That we can kind of measure the relative frequencies of the numbers by a kind of a graph. Right? So we can plot the values that we're interested in this case 0, 1, 2, 3, 4, 5, and we can compute the relative frequencies of these various numbers. This is something you could do. And perhaps, so here would be the frequency, which is really much the same as the probability. So maybe you find that, that you get something like this. In fact, you can try. You probably do get something like this. Okay? That there's some frequency that's sort of maximum, maybe 3 minutes or 4 minutes or 2 minutes. And that as you keep going, the numbers tail off. They become relatively small. There's a kind of a shape to this distribution. And if you perform some completely different experiment, like maybe next time you're at the checkout counter in a department store, you count how many people there are in front of you. That's a completely different experiment. But you might find that the distribution that you get looks a lot like this distribution. Maybe, maybe not. So there are all these distributions out there in the real world that are only accessible to you if you're willing to make measurements over a period of time. But if you are willing to make measurements, you can start seeing these distributions in practice. All right, today we're going to talk about some distributions, some very common ones that occur quite a lot. And one of them is the binomial, which was sort of familiar to you. Another one's called the geometric distribution. And I might talk very briefly about one that looks like this, this one is pretty close to looking like what's called a Poisson distribution. It's another special distribution. All right, so let's have a look at the binomial distribution. And let's ask the simple question of, if we flip a coin, if we toss a coin, n times, what's the probability of getting k heads? Getting exactly k heads. So if we toss a coin n times, then we can express the result of that by a sequence, maybe heads, heads, tails, tails. So there's a sequence of n different h's and t's. Altogether, there are 2 to the n such possible strings. If we assume that the coin is a fair coin, it's equally likely to land heads or tails, then each of these 2 to the n possible strings are equally likely. No one string is more likely than the other. We have a uniform distribution. And so to count the probability that having k heads, we have to ask, well, how many of these strings have exactly k heads in them? All right. So if we call this probability, let's call it, say, p sub k. Well, then p sub k is going to be a ratio. On the bottom is going to be 2 to the n, because that's the total number of strings. And on the top, we have to count the number of strings that have exactly k heads. And that's just counting the number of ways of choosing k out of n positions. So it's k, choose n. That's the number of strings that have exactly k heads. Because you can put the k heads in any one of k choose n places. So this actually defines a probability distribution. This defines what's called a binomial distribution. Okay, the values that we can get are anywhere from 0, 1, 2, up to n. Those are the xi's in our language. And the probabilities are given by these p sub k's. So p sub k is the probability of getting an outcome k. And that's k choose n over 2 to the n. And there's one such for each number from 0 to n. And we can graph this. So for example, here's a somewhat accurate graph, as best as I can here. When we have, say, n equals 10 flips. Okay, so this is sometimes called B10, and there's a half. We'll see what the half is shortly. This is a distribution. So it has values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And along this scale are the probabilities. And maybe I'll put 0.1 here and 0.2. Okay, so the biggest probability is at 5. The probability at 5 is just a little bit more than 0.2. The probabilities of 4 and 6 are equal. They go up to about 0.2. The probabilities of getting 3 and 7 are equal to about 0.12. Something like that. The probabilities of 2 and 8 are about half of that. And the probability of 9, and 1 is about like this. And the probability of getting 0 or 10 is almost invisible on this graph. All right. So these heights are telling you what the various probabilities are. Question?
Although it's combination, isn't it NK?
N choose K. Yes, of course it is. N choose K. Thanks for that correction. All right. The number of ways of choosing K from N is N choose K. Upside down dyslexia, perhaps. Great, thank you. All right, there's the right formula for the P sub K. And here then is a rough estimate of this probability distribution. Okay, this is all very good, but in many situations, we are not flipping a fair coin. Okay, if you're flipping a coin, most coins are fair. But there are a lot of situations where there are two things competing and they're not equally likely. All right? So there's a more sophisticated version where we build in this asymmetry between the two possibilities. So more generally, we flip a coin, flip a, say, P-weighted coin. And that means that the probability of a single head is P. Not necessarily a half. Could be a half, but it could be some number between 0 and 1. In that case, the probability of tails is 1 minus P, and it's often convenient to introduce Q to mean 1 minus P. So with this more general situation, the probability, P sub K, the probability of getting K heads in N tosses is, it's the same situation as before. We have, say, N spots, and we have to put heads, tails, tails, heads, and so on, up to tails. There's altogether N positions. There's still N choose K possible ways of choosing K heads. So there's still N choose K ways of choosing those K positions for the heads. But now the probabilities of these strings are not all equally likely. Okay? So if we have a situation where we have K heads and N minus K tails, then the probability of that happening will be, well, it's going to be P times P times P, 1P for each of the K possible places where the heads can occur. And we have to multiply by 1 minus P times 1 minus P, as many as there are tail positions. That's N minus K. So in the case when P is equal to a half, well, this all simplifies to just 1 over 2 to the n. But when n is not, when P is not equal to half, it's a little bit more general. All right? So this gives P, we still get values, we still get probabilities, P0, P1, Pn are the probabilities of the values 0, 1, 2, up to n. This distribution is called B n NP. Okay. It's called a binomial distribution with there's n positions and the probability is P. And let me show you what it looks like for another kind of value. So for example, if we're looking at B10 0.3, then the distribution of values 3, 4, 5, 6, 7, 8, 9, 10. Point 2 and point 1. In this case, the maximum is just around 3, and then it's a little bit lopsided. So these probabilities represent the probability of getting k heads if the probability of getting one head is 0.3. So maybe it's better not to think in terms of a weighted coin, but think in terms of a competition between two sports teams or tennis players. Okay? If you and your friend play tennis regularly, but if your friend is considerably better than you, so maybe your friend is better so that on any given day, your probability of winning is 0.3 and his probability of winning is 0.7. All right? Then what this is saying is that if you play 10 matches, the probability that you win 5 matches is, well, 0.16. The probability that you win 2 matches is 0.17. So these numbers then tell you what the probability that you're going to win k matches out of 10 in this case, given that your probability of winning 1 match is 0.3. So this is P equals 0.3. Okay, there's a theorem that tells us what the mean and the variance of this general binomial distribution are. The mean and variance of the binomial distribution BNP are, the mean is n times p, and the variance, usually or often denoted by sigma squared, is n times p times 1 minus p, or in terms of n and p and q, n times p times q. So for example, in this situation, the mean would be 10 times 0.3, which would be 3. So this value here is actually the mean. That's actually the place where the whole thing balances. That's your average number of heads that you're going to get if you play this a long time. And the variance, sigma squared, which is the variance, well, that's going to be 10 times 0.3 times 0.7. 10 times 0.3 times 0.7, so that's 10 times 0.21 or 2.1. And the standard deviation That's the standard deviation. That's going to be the square root of that. It's going to be square root of 2.1, whatever that is. And that's a sort of a measure of how far dispersed around the mean this distribution is. The bigger the standard deviation, the wider spread out it is. The smaller the standard deviation, the smaller the variance, the closer things are bunched up to the mean. Okay, so in order to prove this theorem, we would have to make a calculation. We have to make a sum. And that's not impossible to do. So for example, to calculate the mu, that's the sum of the values times probabilities. In this case, it would be the sum from I equals 0 to 10. The values are I, or maybe we should use k. Maybe we'll use k. And the probability of k is 10 choose k times 0.3 to the k times 0.7 to the 10 minus k. Okay, that's not an entirely trivial kind of sum, and the variance is even more complicated. But nevertheless, this is an important kind of task in probability. We have a probability distribution which depends, in this case, on a parameter. There's a parameter, in this case the parameter is p. Well, there's also this number n, which is involved. But p is sort of like a parameter. And it's nice to have formulas for the mean and the variance in terms of these various parameters involved in the distribution. And for more complicated distributions, we can get complicated sums like this. So there's a bit of a trick involving some calculus to calculate means and variances. So I'm going to show you this pleasant trick. Well, maybe not a trick, but it's also a way of thinking about things that's useful in other contexts too. It involves something called probability generating functions. All right, we're going to suppose that the probability distribution has positive integer values. So xk equals k. For k equals 0, 1, 2, 3, and so on. And we might even include the possibility of having an infinite number of potential values. All right, to capture the probabilities all at one blow, what we're going to do is introduce what's called a generating function. This is an important idea in calculus that occurs in lots of other places too, not just in probability. So the probability generating function, it's g of t. And it's defined to be p0 plus p1 times t plus t2 t squared, and so on. So we have these various probabilities. P0 is the probability of getting 0. P1 is the probability of getting 1, and so on. And we're going to put them all together in a polynomial or a power series. We're going to introduce this dummy variable t, which just allows us to string this data together as coefficients of this series. And we're going to call this thing g of t, and we're going to call that the probability generating function. Note that if we plug in t equals 1, then we're just getting the sum of all the probabilities, which has to be 1. Because we're assuming that we have a probability distribution. All these numbers are between 0 and 1, and they add up to 1. All right, so here's a theorem that holds in great generality. Okay. So the mean and variance of this probability distribution are mu is equal to g prime of 1. That's the derivative of this function evaluated at 1. And the variance, sigma squared, is g double prime at 1 plus g prime at 1 minus g prime at 1 all squared. So a little bit of calculus is getting at the means and variances via this formula. All right, let's have a look at why this is. So proof, differentiate, and we get g prime of t equals, we just differentiate the series for g of t. We're going to get the derivative of p0 is 0, and then we're going to get p1 plus 2p2 times t plus 3p3t squared, and so on. Just the derivative of this polynomial, or maybe it's an infinite power series. And so if we plug in 1, then we get p of 1 plus 2 times p2 plus 3 times p3. And that's the same as the sum of the values times the probabilities. Because we said that the values were just 0, 1, 2, and 3. So here's 0 times p0 doesn't appear, 1 times p1 plus 2 times p2 plus 3 times p3 plus, and so on. And that's our definition of the mean. All right, that was pretty easy. Now to get the variance, we have to do a little bit more work. So we multiply g prime of t by t and differentiate again. All right, so I'm going to take the derivative right here, and I'm multiplying it by t. So I get p1 times t plus 2p2 times t squared plus 3p3 times t cubed, and so on. And I'm going to differentiate that. And that, maybe I should say, that's t g prime, all prime. Okay, when we differentiate this term by term, we're going to get p1 plus 2 squared times p2 of t times t plus 3 squared times p3 times t squared, and so on. Now set t equals 1. So if I take t g prime prime and I evaluate it at 1, I get p1 plus 2 squared p2 plus 3 squared p3, and so on. we'll just pretend we're keeping on going. And that's the same as the sum from k equals 0 to infinity of k squared times p sub k. Now recall that we started off by saying that the variance had this alternate form, that it could be written as the sum of the values squared times the probabilities minus the mean squared. So that's good, because that's exactly what we've gotten here. This first term is exactly what we just computed here. So what is this derivative? Well, this is a derivative of a product. Let me write that out again. So it's t g prime prime at 1 minus mu squared. And what is that? Well, this is the derivative of a product. So it's the derivative of the first term times the second. So that's just g prime at 1 plus the t times the derivative of the second one. That's g double prime at 1. Because when I replace 1, the t at the beginning just becomes 1. And the mu we've already calculated the mu. The mu we said was g prime of 1. So the g minus g prime of 1 squared, that's just the mu squared that's appearing here. And that's the formula that I wrote down. All right, that's good. So let's see if we can calculate, now using this technology, the mean and the variance of this binomial distribution. All right, so for the binomial distribution, the thing that we're calling BNP, and I remind you that means we are tossing a coin n times, and the probability of a single head is p. Okay, so the first thing we need to calculate is this generating function. So what is the generating function? Well, the definition is that it's g of t. So it's p0 plus p1 of t times t plus p2 t squared, and so on. In this case, it's only going to be a finite sum, because there's only a finite number of values. We're going from 0 to n. So the last one will be n. Well, p sub n plus p sub n t to the n. Okay, so what is this thing? Well, we have to remind ourselves, what is b, what is the p sub k in this case? The p sub k is the probability n choose k times p to the k times 1 minus p, or q, to the n minus k. So this thing looks like what? There's an n choose 0 times p to the 0 times q to the n. And then the next one is n choose 1. And then there will be a p and a q to the n minus 1. And there will also be a t term. And we keep on going. The binomial coefficients get bigger. The powers of p get bigger. The powers of q get smaller. And the powers of t get bigger as well. Until we get to the last term, which will be n choose n. And then there'll be just a q to the n, t Whoop, to the n minus 2, that was supposed to be. Q to the n, t, p to the n. The p's are getting bigger. Sorry, this was a 2. There we go. So the p's are getting bigger. The t's are following also getting bigger one at a time. The q's are getting smaller. Okay, and then when we stare at this for a minute, hopefully we recognize that it's something familiar. P. Okay, what about the T? But you're all pretty well right. PT plus Q to the N? Does that sound reasonable? Because the P, you can sort of put the P and the T's together. So this sort of shows the power of the generating function, that this relatively simple function contains, when you expand it out, all of the coefficients are exactly all the probabilities in the right places. It's a very efficient way of encoding all the probabilities. And of course it makes it relatively easy to calculate the mean and the variance applying this theorem now. So the mu, according to the theorem, is g prime at 1. So we have to differentiate this. N times p t plus q to the n minus 1 times the derivative of the inside, which is p, and we have to evaluate that at t equals 1. Well, when t is equal to 1, we get p plus q here, which is 1. And so we just get n times p. And the sigma squared, well, it's g double prime of 1 plus g prime of 1 minus g prime of 1 squared. So I'm going to leave that to you as an exercise, a little bit of differentiation and such, that you get n times p times 1 minus p. All right, a closely related distribution is the geometric distribution. Let's talk a little bit about that. So the geometric distribution, it's another natural one. So again, we start with a p-value. Let's just keep it between 0 and 1. And we toss a p-biased coin. And the usual convention is that the probability of heads is p. And we toss it continually, actually, until we get a head. Like, if you play the game Trouble, and you have to start by rolling a 6 so you can get your man out. It's like that. You have to keep rolling and rolling and rolling until you eventually get a 6, and then you can start. Okay. So the main thing is, how many times do you have to roll before you get a 6? It's the same kind of thing, but now we're flipping a coin until we get a head. All right, so the random variable is x of s equals k if the first head appears in the kth position. So for example, if we had the sequence T, 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 H, H, T, H, and so on. Okay, if that was sort of our sequence, then the function that we're interested in is where does the first head appear? First head appears in position 4. That's the actual random variable. Okay, there's an underlying population, the population of strings. The function is counting where the first head appears. The possible values are, well, xk equals k, for k equals 1, 2, 3, and so on. And what are the associated probabilities? Well, with probabilities, so what's the probability of getting a head for the first time at position k? What's the probability of that? Well, it means that for all the previous times, you've gotten tail, 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 tail. So the probability of a head is p. As usual, we'll agree that the probability of a tail is 1 minus p, which it will call q. So the probability that we get a head first in the kth position is q times q times q. This altogether k minus 1 times p. So it occurs when the first one's a tail, the second one's a tail, and so on. The first k minus 1 are all tails, and then the kth one is a head. So we can just write q to the k minus 1 times p. Or if we want to write it just in terms of p, it will be 1 minus p to the k minus 1 times p. So that's the formula for the probability p sub k for the geometric distribution. Maybe I'll put the p here. P times q to the k minus 1. All right, what's the generating function? The generating function, we're calling it g of t. So that's going to be p sub 1, which is just p, times t. And then the next one will be 1 minus p. Oh, I might just use q. So that's p. That's the first term, p sub 1 times t. P sub 2 is p times q times t squared, and then p times q squared times t cubed plus p q cubed times t to the fourth, and so on. And this one doesn't end because theoretically you could consider very large values of k as well. All right, fortunately this is a geometric series more or less. You can kind of see that there's a constant term p, and then it's more or less powers of q times t if we multiply by q. So if we write it out as a geometric series, we would get, maybe we could write it as p times t, and then 1 plus qt plus q squared t squared, and so on. That makes it obvious it's a geometric series if we pull out that pt. And so the formula for the geometric series is, starts with 1, ratio of q times t. So the infinite series has power series 1 over 1 minus qt. So pt over 1 minus qt, that's the generating function for the geometric series. And then I'll leave it to you as an exercise, a bit of calculus theorem, that the mean then is 1 over p, and the variance is q over p squared. In particular, if p happens to be 1/6 and you're playing trouble, so you're really only interested in whether you get a 6 or not, the chances of getting a 6 is 1 out of 6. It's like tossing a coin that's a 1/6 weighted coin. This is telling you that the expected value, the number of times that you should expect to have to roll before you get a first 6, is 1 over the probability. The probability is 1 over 6, then you're going to get an expected value of 6. So you have to expect on average that you're going to have to roll 6 times to get that first 6. Okay, so next time I didn't get to the sign test, I'll talk about sign test, a little bit more about maybe binomial applications to the sign test, and then we'll move towards continuous distributions and the normal distribution.